Dear students, welcome to the second lecture of Module 2 Fourier Series. In the last lecture, we have started the Fourier Series. In this lecture, we will study how to obtain the Fourier Series of periodic functions which are either even or odd. Before we see what are Fourier Series for even and odd functions, let us recall the definition of Fourier series for the periodic function in the interval minus L, plus L. The Fourier series is f of x equal to a0 by 2 plus summation n from 1 to infinity a n cos n pi x by L plus summation n from 1 to infinity bn sin n pi x by L, where a0, an, bn are given by Euler's formulae. Formula for a0 is equal to 1 by L integral from minus L to L f of x dx, and an is equal to 1 by L integral from minus L to L f of x cos n pi x by L dx. Bn is equal to 1 by L integral from minus L to L f of x sin n pi x by L dx. In the first lecture, we have studied how to calculate by integration these Fourier coefficients a0, an, bn. Sometimes these a0, an or bn become 0 after integration. Finding zero coefficients in such problems is time consuming and can be avoided with the knowledge of even and odd functions. A zero coefficient may be predicted without performing integration. Now, what are even and odd functions? A function f of x is said to be even if f of minus x equal to f of x. For example, x square, cos x are even functions. Here, how do you check cos x is even? We take f of x equal to cos x, then f of minus x will be cos minus x, and cos minus x is same as cos x. So, we get f of minus x equal to cos x. So, cos x is even. Then, function is said to be odd if f of minus x equal to minus of f of x. So, examples for odd functions, we can take x cube, sin x, etc. Next, let us look at two properties for definite integrals for even and odd functions. If f of x is even, then the value of definite integral minus L to L f of x dx is 2 times the value of integral 0 to L f of x dx. Also, if function is odd, then the value of integral minus L to plus L f of x dx is equal to 0. Also, the product of two even functions or two odd functions is an even function, whereas the product of an even function and an odd function is an odd function. If you look at the first example, we have x square is an even function, cos x is an even function. So, the product x square cos x is also even. Next, we will use all these properties of even and odd functions, and we will see what happens to the Fourier series for the case of even and odd functions. Now, suppose f of x is even. Then, Euler's formula for a0 is 1 by L integral from minus L to L f of x dx. If f of x is even, then the integral minus L to L will be equal to 2 times integral from 0 to L f of x dx. So, formula for a0 will be 2 by L integral from 0 to L f of x dx. Similarly, an formula is 1 by L integral from minus L to L f of x cos n pi x by L dx. Now, if function here we have cos n pi x by L is an even function, and if f of x is even, then the product f of x into cos n pi x by L will be being the product of two even functions. The product will be even function. So, from the property of definite integrals, we can write minus L to L, integral minus L to L can be written as integral 2 times integral 0 to L, 2 times integral from 0 to L. So, we can write an will be equal to 2 by L integral from 0 to L f of x cos n pi x by L dx. Next, formula for bn, we have 1 by L integral from minus L to L f of x sin n pi x by L dx. Sin n pi x by L is an odd function f of x. If f of x is even, this becomes the product of even and odd function. So the product will be odd function. So value of bn or value of the integral will be 0 for odd functions. So we have bn will be equal to 0. And the Fourier series for even functions, we get f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L. Here note that an even function has only cosine terms in its Fourier series expansion. Now suppose f of x is odd. In this case, formula for a0, that is a1 by L integral from minus L to plus L f of x dx will be 0. By the properties of integral, function f of x is odd means this integral will be 0. That is a0 will be 0. Similarly, an formula 1 by L minus integral minus L to L f of x cos n pi x by L dx. If f of x is odd, so this integral becomes the product of odd and even function. That is, this product will be odd. So integral minus L to L of odd function will be 0. That means an will be 0. Next, bn is equal to 1 by L integral from minus L to plus L f of x sin n pi x by L dx. Here f of x is, if f of x is odd and we have sin function is sin n pi x by L is odd function. So this becomes product of two odd functions. We have even function. So integral from minus L to L can be written as 2 times integral from 0 to L. The formula for Bn will be 2 by L integral from 0 to L f of x sin n pi x by L dx. So Fourier series will be f of x equal to summation n from 1 to infinity Bn sin n pi x by L. Here note that an odd function has only sine terms in its Fourier series expansion. Now suppose we need to find the Fourier series expansion for functions defined in the interval 0, 2L. Then we make use of these definitions of even and odd functions in the interval 0, 2L. A function f of x is said to be even in the interval 0, 2L if f of x satisfies the condition f of 2L minus x equal to f of x, and function is odd if f of 2L minus x equal to minus f of x. Also, the definite integrals satisfy these two properties. The first property says if f of 2a minus x equal to f of x, then the value of integral from 0 to 2a f of x dx will be equal to 2 times integral from 0 to a f of x dx. And if f of 2a minus x equals to minus f of x, then the value of integral from 0 to 2a f of x dx will be equal to 0. Using all these results, we can prove that for any even function f of x in the interval 0, 2L, a0 formula is given by a0 is equal to 2 by L integral from 0 to L f of x dx. An will be 2 by L integral from 0 to L f of x cos n pi x by L dx, and Bn will be equal to 0. The Fourier series for even function will be f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n pi x by L. Similarly, for the odd function defined in the interval 0, 2L, what are a0, an, b? a0 will be 0, an will be 0, and bn will be 2 by L integral from 0 to L f of x sin n pi x by L dx. The Fourier series for an odd function is f of x equal to summation n from 1 to infinity bn sin n pi x by L. Here note that for function defined in the interval can be minus L to L or 0 to L, Fourier series will be same, and formula for a0, an, bn will be same for even and odd functions. Now let's solve some problems on Fourier series. So first problem, express f of x equal to 1 minus x square as the Fourier series over the interval minus 1 comma 1. Here note that the given interval is of the form minus L comma plus L. So comparing with the interval minus L comma plus L, we have L equals to 1. So first find, before finding the Fourier series, first find whether the given function is even or odd. If the function is even, then we need not calculate Bn. Bn will be 0. And if function is odd, then a0 will be 0 and an will be 0, and we need to find then only Bn. So first find whether function is even or odd. So how do you check whether function is even or odd? We take f of minus x. If you find f of minus x equal to f of x, then function will be even. If you get f of minus x equal to minus f of x, then the function will be odd. So here take x equal to minus x, you will get f of minus x equal to, the function takes the form f of minus x equal to 1 minus x the whole square, that is 1 minus x square. So we get back to the function f of x, 1 minus x square equal to f of x. So function is even, hence Bn equal to 0. So what is the corresponding Fourier series? Fourier series will be f of x equal to a0 by 2 the summation n from 1 to infinity an cos n by x by L. Next, what is the value of L? So L is equal to 1. Substituting for L equal to 1 in the Fourier series, we get f of x equal to a0 by 2 plus summation n from 1 to infinity an cos n by x. Next, we will find a0 and an by using formula, the Euler's formula for even functions, and substitute back again in this Fourier series. So formula for a0 is 2 by L integral from 0 to L f of x dx. Substitute for L and f of x. L is equal to 1 and f of x given function we have 1 minus x square. Integrate. Integral of 1 is x, integral of x square is x cube by 3. Substitute the upper limit x equal to 1, then put x equal to 0, simplify, we will get a0 equal to 4 by 3. Next we will find an. Formula for an is 2 by L integral from 0 to L f of x cos n by x by L. We have L equal to 1 and f of x equal to 1 minus x square. So this is equal to 2 into integral from 0 to 1, 1 minus x square cos n by x dx. So here we have it is of the form integral uv, and we have Bernoulli's rule of integration by parts. Integral uv dx equal to u v1 minus u dash v2 plus u double dash v3 minus etc. We apply this rule for this integral, taking u equal to 1 minus x square and v equal to cos n by x. We get an equal to 2 into, so first term we have u v1. U is 1 minus x square, v1 integral of cos n by x, that is sin n by x divided by n pi, minus u dash. U dash is derivative of u, that is derivative of 1 minus x square minus 2x, and v2. v2 is integral of v1, integral of this sin n pi x by n pi is cos n pi x minus cos n pi x divided by n square pi square. Next we have next term u double dash v3, u double dash derivative of u dash, that is derivative of minus 2x minus 2x minus 2, and v3 integral of this minus cos n pi x by n square pi square is minus sin n pi x by n cube pi cube. Then substitute the limits x from 0 to 1 and note these 2 points. At x equal to 1 upper limit sin n pi is 0. So that is the first and last terms will become 0, and at the lower limit x equal to 0 we have sin 0 equal to 0. Again at the lower limit the first and last terms will be 0. So apply the limits for the second term only. So we'll have an equal to minus 4 into minus 1 raised to n by n square pi square. Here note that the value of cos n pi is minus 1 raised to n. Then we substitute the values of a0 and an in the Fourier series. We get f of x equal to 2 by 3 plus summation n from 1 to infinity minus 4 minus 1 raised to n by n square pi square cos n pi x as the required Fourier series expansion. Next problem, express f of x equal to x by 2 as a Fourier series in the interval minus pi plus pi. So here, given function, first find whether the function is even or odd, and we have the given interval is minus pi to pi. It is of the form standard interval minus L plus L. So comparing, we get L equal to pi. Now to find whether given function is even or odd, take x equal to minus x. We will get f of minus x equal to minus x by 2 or minus f of x. So here we have function is odd. Therefore we can write a0 equal to 0, an equal to 0. Okay, we need to find only bn. So what is the Fourier series for given function? General Fourier series is f of x equal to, since function is odd, general Fourier series is f of x equal to summation n from 1 to infinity bn sin n pi x by L. Now here L is equal to pi. If I put L equal to pi in the general series, L cancels with the pi there. So if you put L equal to pi, L or pi cancels. So we are left with the f of x equal to summation n from 1 to infinity bn sin nx. So formula for bn, general formula 2 by L integral from 0 to L f of x sin n pi x by L dx. Put L equal to pi. So pi cancels in the numerator and denominator. Then we will get this formula, that is bn equal to 2 by pi integral from 0 to pi f of x sin nx dx. Then substitute for f of x. We will have 2 by pi integral from 0 to pi x by 2 sin nx. 2 cancels there. So we have integral x sin nx dx. Okay, so it is of the form integral uv. Okay, u equal to x, v equal to sin x. Apply Bantwal's rule, integrate. We will get 1 by pi into x into minus cos nx by n minus 1 minus sin nx by n square. Apply the limit 0 to pi. I will get bn equal to minus 1 raised to n divided by n. Okay, now substitute in the Fourier series. We get f of x equal to minus summation n from 1 to infinity minus 1 raised to n by n into sin nx. Okay, this is our required Fourier series expansion. Now look at this problem. Question number 3. Obtain the Fourier expansion of f of x. See here, function is defined in the two intervals. So it is a interval for interval 0 to pi. F of x is defined as x, and in the interval minus pi to 2 pi, function is defined as 2 pi minus x. And we need to find the Fourier series in the interval 0 to 2 pi. See here, 0 to pi and pi to 2 pi. So function is defined over the interval 0 to 2 pi. We need to find the Fourier series over the interval 0 to 2 pi. And we need to deduce the series. Pi square by 8 equal to 1 plus 1 by 3 square plus 1 by 5 square plus etc. Now here function is, so we will find L here. So to find L, compare the interval 0, 2 pi. Function is defined over the interval 0, 2 pi. So compare this with the standard interval 0, 2L. So we will get a 2L equal to 2 pi, L equal to pi. Now how do you check the function is whether even or odd? Okay, here function is defined over interval of the form 0 to 2L. We take f of 2L minus x and find whether f of 2L minus x equal to f of x or minus f of x. If f of 2L minus x equal to f of x, then it is even. If f of 12 minus x equal to minus f of x, it is odd. So here it is, we can make out clearly function is even. Okay, it satisfies the condition f of 2l minus x equal to f of x with l equal to pi here. So we have f of 2 pi minus x equal to f of x, function is even, bn equal to 0. So we can write Fourier series as f of x equal to a0 by 2 plus summation n from 1 to infinity an cos nx. Find a0. A0 is equal to 2 by pi integral from 0 to pi f of x dx. So substitute for f of x. Here f of x is, okay, f of x is equal to x. So function f of x equal to x in the interval 0 to pi. And integrate, apply the limits, we will get a0 equal to pi. Then we will find an. An is 2 by pi integral from 0 to pi f of x cos nx dx. Substitute for f of x and integrate, we will get an equal to 2 by pi integral from 2 by pi minus 1 raised to n minus 1 by n square. Substitute the values of a0 and an in the series. So this is our required Fourier series expansion. Now to deduce the series, given series in the problem, so we take x equal to 0 on both sides. So here right side will get cos 0 1. Okay, so this will be 1. So we will get summation containing 1 by n square terms. So left side f of 0, what is f of 0? So function is defined as x for the interval 0 to pi. So for x equal to 0, f of 0 is 0. Okay, so we have in the next step, okay, we will get this. So f of 0 is 0, right hand side, okay, here 2 by pi, constant, take outside the summation and expand the summation, take n equal to 1, 2, 3, etc. in the summation and simplify, go on simplifying. Okay, so we will get pi square by 8 equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square, etc. The required series given in the problem. Now for the next question, function given is f of x equal to 5 plus x for the interval minus pi to 0 and f of x is defined as pi minus x for the interval 0 to pi. Here we need to find the Fourier series. Also we need to reduce the series pi square by 8 equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. So here what is L? So function is defined over the interval minus pi to pi. So compare with the standard interval minus L comma plus L. So we will get L equal to pi. Okay, so here we can make up, it is clear that function is, if you replace x by minus x, we get f of minus x equal to f of x. So function is even. So a0, bn will be 0, we need to find a0 and an. And Fourier series is given by f of x equal to a0 by 2 plus summation an cos nx, and find a0 and in the formula just note this, in the interval 0 to pi what is f of x. So here given in the interval 0 to pi f of x is defined as pi minus x. So what is f of 0? F of 0 is f of x is, so in the interval 0 to pi f of x is pi minus x. So replace f of x equal to pi minus x. So here integrate, apply the limit, a0 equal to, we will get a0 equal to pi. Then find an is equal to 2 by pi integral from 0 to pi f of x cos nx dx. Substitute f of x equal to pi minus x and integrate, we will get an equal to minus 2 by pi into minus 1 raised to n minus 1 by n square. Okay, substitute these values of a0 and an in the Fourier series. So required Fourier series is f of x equal to pi by 2 plus summation n from 1 to infinity minus 2 by pi minus 1 raised to n minus 1 by n square cos nx. Next, okay, take again here we have 1 by n square terms. So take x equal to 0, make it 1. Cos 0 is 1. So take x equal to 0, f of 0 equal to pi by 2 plus summation. Okay, minus 2 by pi minus 1 raised to 1 n minus 1 by n square. So in the next step, we will get this and substitute for f of 0. What is f of 0? F of 0 is function. Notice function f of x is pi minus x. Okay, for the interval 0 to pi is given in the problem. So, what is f of 0? F of 0 is pi minus 0. So, that is f of 0 is pi. Substitute for the left hand side and right hand side minus 2 by pi. Take outside the summation. Simplify the terms by taking n equal to 1, 2, 3, etc. Okay, so we get pi square by 8 equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square, etc. So students, in general, to find Fourier series of any function, first find whether the given function is even or odd. If a function is even, then we don't need to calculate Bn. And if a function is odd, then no need to find a0 and an. But if the given function is neither even nor odd, then we need to find all a0, an and bn. So students, this is all about Fourier series of even and odd functions. Thank you.